Okay, we're officially recording. And then before I hand it off to Lisa to introduce JPL's Planetary Protection Center of Excellence, is there any questions from the NASA Space Biology or GeneLab overview from this morning? You guys can either type in the chat or mute your mic. No questions? Okay, great. In that case, Lisa, I'll hand it off to you to give us an introduction on planetary protection. I'm going to go ahead
Okay,
and
thank
share
you.
your screen.
Yeah. Good. Can you all see this okay?
Yeah. And then Lisa,
Okay.
if you go up to your share where it says where you could stop sharing, if you just click on the chat icon, you'll be able to pull up the chat too and see it.
Yeah, I got the bubble up. Thanks.
Excellent.
Okay. So I have the PDF version here. I'm not sure if there was any animation in the PowerPoint, but I think it should be fine. Hi everyone, I'm Lisa again. Armand prepared these slides, but since he's out sick, I'm going to go ahead and present them. If there are any questions that you have that I can't answer, we'll be sure to pass them on to him when he's back. Okay. So quickly, brief history of JPL. JPL was founded in the 1930s by a few Caltech students who were testing rocket motors in Pasadena. And it's actually it was founded earlier than NASA, and in the late 1950s, it joined NASA as a federally funded research institute. And so we're federally funded, but we're governed and managed by Caltech. And right now, there are about 5,000 employees, and especially in the summertime, with student interns, we can have over 1,000 students. And there are lots of active missions going on. There are a few listed here: Juno, Cassini, well, not Cassini anymore. Cassini as of a few years ago, MRO, Mars Sample Return, Mars 2020, Dawn, Europa Clipper, InSight, and now Mars Sample Return. And so in my time at JPL, I have worked planetary protection on InSight and Mars 2020. And right now I am the planetary protection lead for our Europa lander concept mission. And so I'll talk a little bit about that. And so what is planetary protection? Our aim is to protect other worlds from microorganisms found on Earth, and that's forward planetary protection. But we also have backward planetary protection goals, which is to control and prevent any harmful microbes from coming back to Earth with any missions that we have returning. And the reason why is because to protect the integrity of our scientific objectives with our missions. And so how can we look for life on other planets if we bring our own? Especially with our current missions and planned missions in the future, the instruments that we'll be bringing along are incredibly sensitive. And so we want to make sure that they are built and assembled and launched in the cleanest environment possible. And so we have planetary protection requirements that are from NASA headquarters, and they comply with international treaty obligations. And the treaty that is being referred to here is a UN treaty from the 1970s. And so here's some examples of a planetary protection requirement. This is specifically for a Mars-bound, biologically sensitive mission. And so the requirements for a Mars mission of this type would be a spore quota. So we would need less than 5 times 10 to the 5 total spores at launch, less than 3 times 10 to the 5 spores on planned landing hardware, and overall less than 300 spores per meter squared for exposed surfaces. In the example of Mars 2020, which was with our Perseverance rover, it was the biggest rover that we've ever sent with a lot of complex hardware. So actually, if we were to meet the requirement of 300 spores per meter squared, given how large all the surface areas are, we would actually surpass the 5 times 10 to the 5 total spores at launch and 3 times 10 to the 5 on landing. And so we had to be cleaner than 300 spores per meter squared for most of our surfaces. And so for each mission, we develop a biological contamination control campaign. And this actually begins way before any hardware is manufactured or assembled. So for example, I work on the Europa Lander concept mission, and we are in pre-phase A, so we're not even a project yet, but planetary protection is heavily involved because it is such an integral part of a mission to Europa, for example. And so they include, we are involved in hardware design, material selection, material processing, and even landing site selection. And then, of course, we are part of the assembly, test, and launch operations. And so once the hardware does start getting assembled, we monitor microbial bioburden and perform additional reduction processes if needed. And we generally do this with wipe and swab samples, and currently still use a cultivation-based method or the NASA standard assay to measure heat-tolerant organisms, and use that as for Mars missions, that's actually our quota. For other missions, we're currently using that as kind of a measurement of or proxy for all types of microbes that could be present on the spacecraft. I see a question, what criteria established this number? That's a good question. That's a good question for headquarters. Unfortunately, I don't think that we have the sources for how these were determined, because these were probably determined a long time ago in the 70s when these requirements were first written. However, NASA is in the process of updating this requirements document 80/2012D, and so we should have more clarity on how the new requirements would look. And so this is an example of our implementation process. So first we clean, then we swab or wipe to see how clean, and maybe we need to do it again if it's not clean enough. And then we use protective covering, such as you can see these Amerstat bags that are being used to cover the spacecraft to keep it clean. And there are just routine cleaning processes, including of the facility and of the spacecraft, of the exposed surfaces throughout the assembly process. And so this is just a bit more detail about our NASA standard assay. And so with our clean hardware, we will swab or wipe using water, and then bring it back to our lab. For the samples are heat shocked at 80 degrees Celsius for 15 minutes, and then plated onto tryptic soy agar plates. And then we count and check for positive growth for up to 72 hours. And so this assay detects spores specifically because they are heat resistant, and those that are viable, cultivable, and aerobic because we are growing them at 32 degrees for 3 days. And it does not detect non-cultivable vegetative cells grown under various conditions that are not aerobic and 32 degrees Celsius. And so it is underestimating the total microbial bioburden. This is an Armand side, and it's a project that he is working on right now to determine the sampling size and bioburden accounting. And so essentially looking at the statistics for how we apply what we observe in our samples to the entire spacecraft. And so I am going to move on from this slide because I'm not familiar with that project, but we can ask him about it when he's back. And if we see positive growth on our plates following culture, there are several ways that we can identify the colony. And one of them is 16S RNA sequencing, because 16S RNA is a highly conserved gene and can be used for phylogenetic classification of bacterial isolates at a species level. And if we find a 97.5% sequence similarity, then we would say that we identified this isolate at a species level. And anything higher than 95% match, we would say that we identified the isolate to a genus level. And currently we are still working, we've sequenced a handful of Mars 2020 isolates, and we are working on sequencing more. And another way that we identify the microbes that we isolate are MALDI-TOF or mass spec. And so these are sometimes used in tandem, but a lot of the times we default to MALDI because it is so fast. We can get results, we subculture from the plate where we observe the positive growth, and then we can get results within a day. And currently, the microbial archive that we have of the isolates that we've collected from the spacecraft surfaces, it goes back to the Viking mission. And so this is a really extensive archive that we have going all the way back to the 1970s. And as you can see here, Mars 2020 is the largest contributor to this culture collection. And so now just talk a bit about MALDI. So MALDI is matrix-associated laser desorption ionization time of flight mass spectrometry, which is called MALDI for short. It generates ions from large molecules while minimizing fragmentation, and the identification process is based on a protein profile that the MALDI machine generates. And so this is the process for preparing the sample for MALDI. It involves inoculating 2 loops of biomass into 1 ml of 75% ethanol, vortexing for 15 minutes, pellet the isolate, decant the ethanol, and add 1 microliter of the supernatant to the target and overlay with matrix. So this is the plate that will get inserted or be read by MALDI-TOF. We add 100 microliters of 100% acetonitrile and centrifuge for 2 minutes. Oh, sorry, the other way around. With the pellet, we add formic acid and acetonitrile, and then that gets loaded onto the plate to be read. And the reading is incredibly fast. I think it's seconds per target. I think this plate can hold 96 targets, and so it's a matter of minutes for the spectra to be generated. And the goal is to rapidly identify bacterial colonies at the species level. Isolates are analyzed by mass spec in replicates of 4 or more. We do get different IDs sometimes within the 4 replicates. And so sometimes we have to do more than 4. The resultant spectra are compared to databases, including one of our own that we've built using using isolates from previous missions, identifying with either 16S or whole genome sequencing. And so we have kind of this clean room isolate internal database, but we also do compare it to the Bruker database. So Bruker is the company that produces the instrument. Identifications and scores are examined to determine the confidence of our ID. and these IDs are used to trace and mitigate contamination. And so this is our scoring strategy here. So like I said, we start with 4 replicates, and the score that is on the second column here, the score is how well it matches to a spectra in any of our databases. And so if a score above 2.2 is considered a good match, and so if we have 3 out of the 4 that score above 2.2, we're considered confident in identification, and we call it a perfect ID. A lot of the times we do have, a mix of high scores and low scores, and sometimes it is, for example, in this bubble here, we'll see that in March M2020 sample 2167 had high scores in a couple of replicates and a lower than 2.2 in one of them, and however it's still pretty close, but it is a different species of bacillus. And so in this case, we would call it a taxonomic group, where the scores are all above 2.0 with a genus identified but mismatched species. And so in cases like this, we may send it out for 16S sequencing or whole genome sequencing, depending on how similar the species are within these group. So this slide was provided by Akemi Hinzer, who was a student in our previous last year's Voices program. And so following her the workshop, and she did the 5-week internship, she joined our group as a year-round intern. And so what she did is previously we did all this by eye. We would just look at the 4 matches and then determine, okay, well, did it meet any of these criteria? And it can be a lot because, as you saw in the previous slide, we have thousands of samples. And anytime we update the database, anytime we generate new spectra from, whole genome sequencing, we would want to rerun everything that we've done before. And so what tends to happen is you get a backlog of samples that still need to be analyzed by people. And so what Akemi did following her Voices internship was apply the programming knowledge that she learned, and she actually wrote a program to automate all this. And so now we can identify or correctly assign IDs from MALDI results in about minutes. And so Akemi is a real Voices success story. So I'm really proud of that. Oh, yeah, so I already mentioned this. The mass spectra that we generate are compared against the Bruker reference and at JPL in-house curated database. And so here are some of our preliminary findings. So of the, for Mars 2020 anyways, a total of 16,839 samples were collected, and out of those, 1,686 plates produced colonies. And from those positive plates, 4,232 colonies were subcultured and archived because some plates had more than one colony. And this is hidden by the bubble, but we've analyzed 3,101 isolates, and I think the bottom number is however many were perfect IDs. I think it's around 1,000 that were perfect IDs. But here's some characteristics of the isolates that we have ID'd so far. There's a question about Akemi. She did all of this by herself. Essentially, yeah, Akemi did a really, really great job. So her and I worked really hard on kind of developing the criteria needed to the logic anyways of kind of, how many scores are needed. What do you do if you have more than 4? I think the default is 4, but sometimes you have 12, sometimes you have 16. And so kind of just working through all the different ways that her script could break. Armand helped us define, the relevant groups and what kind of categories we should make. And so it was a group effort, but the scripting was and the coding was all Kemi. And so the chart on the right here is a distribution of the various genera that we found on the spacecraft and not on the spacecraft. And what's interesting to point out here is that so anything that's not spacecraft was either facility samples or ground support equipment samples. And so what the point to make here is that we see a lot of similarities between what we find in the facility and what we find on the spacecraft, which is to be expected. But what it does is, justify maintaining the strict cleaning procedures for the clean room. And so the preliminary findings, they're preliminary because we still have more samples to identify for Mars 2020, but essentially you can see here that the most common genus was Bacillus. However, we did find some Staphylococcus, which is not a spore-forming organism, but we tended to this chart here shows that we actually did find a lot of instances of staph in our samples. And so what if there are no matches to known sequences? It could potentially be a novel species. And so some of the more interesting novel species that have been found include Pennybacillus xerotherodermans here, which is an extremely dry heat resistant spore forming bacteria. I think one of the most dry heat resistant bacteria out there. Another one that is also dry heat resistant is Bacillus canaveralis, named after Cape Canaveral, where it was isolated from. And what's cool about these species that we've isolated is that we are now using them as indicator organisms for developing our heat microbial reduction standards. And NASA headquarters is also using them for that. So they'll use that to actually write, the time and temperature requirements for heat sterilization. I got a question. Did you look into the heat resistance of the staph isolate? That's a great question. I don't think we have yet, but that would be really interesting to look at. And we've also found a novel genera, and so Parag was part of this work. I don't think Parag is on anymore, but definitely reach out to him if you have questions about this. And I think that was the last slide. Are there any questions? If not, I will pass it back to Amanda. Thank you.
Great. Thanks so much, Lisa, for impromptu taking over our slides and doing a great job presenting an overview of JPL's planetary protection and some of the awesome data and work that you guys have done. Going back to sharing my slide. So from that pre-bootcamp survey, I noticed that quite a few of you are very new to the command line and running commands. So I do want to preface this that we are not going to expect you to walk out of a week and a half long boot camp being a coding expert by any stretch of the imagination, but we're hoping to at least give you some background about the syntax, how commands are set up, some of the basic commands that are run when running and looking at RNA-seq data. And so these next several slides that we'll get into before lunch is going to kind of walk us through the command line, how to run commands, what those look like side by side with some user interfaces that you guys are probably more comfortable using, like Finder. And then when we get back from lunch, we'll log into the NCCS SMCE system, which is where we're going to be doing all of the hands-on portion of this boot camp, and we'll start running some of the commands that I'm about to go over with. So please feel free to ask questions as they come up. If you guys are comfortable, you can go ahead and send your question to everyone in the chat, because some people might have the same questions as you, and also just in case whoever's presenting might miss something. So if you guys are comfortable sending your questions to everyone, that would be great. Of course, if you're not comfortable, you can always send it specifically to one of our instructors. Wait, so that said, I'm going to get into this introduction to the command line. And there was a small amount of you that do have some pretty good experience running commands. So for that one person or two, this part might be a little boring. For the rest of you, hopefully it'll be useful. So first, some terminology. What is a terminal? A terminal window is a command line interface that's going to be used to interact with your computer. It usually doesn't contain graphics. And this terminal window will display a blank text window or a command line where you can type commands that allow you to communicate with your computer. You see an example of it depicted in the image at the bottom of my screen. And the terminal is going to use a specific language interpreter or a shell to interpret the commands that are being typed into the command line. And the Unix is a computer operating system that's written in the C programming language. And by default, terminals on both Linux computers and Mac computers run a Unix shell. You can also download software to be able to run a Unix shell on a Windows computer as well. Unix shells do come in a variety of different flavors. ZSH, CSH, TCSH, and Bash are some common ones. They each have slightly different features and functionality. For this boot camp, we're going to be using the Unix shell simulator Bash when we run our commands throughout the boot camp. So just getting into some command syntax. So general command line syntax goes as follows. So you type the name of the command followed by any arguments for that command. Depending on which command you use, these arguments can be optional or they can be required in order to run the program. And I just want to note here that arguments can also be referred to as options, parameters, or flags, and you'll hear me use these terms interchangeably. So all available arguments for a command is going to be able to be found by looking at the command's manual or help page, which can be found online. It also can be opened in the terminal. So to view a command's manuals, we can use the man function on the Unix terminal, followed by the command of interest, the command for which we want to see the help menu. I do want to point out that this man command is not usable on the system we're going to be using for the boot camp, but on your own computers, it will be available. So in the example, you would type man and then whatever command you want to look up the manual. Another option, which we will be doing during the boot camp, is to view the command's help page. You can use the --help or -h flag for the command of interest. So that'll look like the command of interest followed by --help or -h, depending on how that program is set up. So below is the manual of a common Unix command called mkdir. We're going to be running this makedir command in the boot camp. And the manual that I'm about to show you is displayed in a terminal, and it was brought up by running the command man and then mkdir. So man for manual, and then mkdir is the program that I want to see the manual for. And then I'll just walk you through some of the things that we see here. So in that synopsis section of the makedir manual, we'll show how the command should be run. So you notice that this command, you would start by typing mkdir. You'll see some flags indicated in the brackets, and then the command should end with a directory name. So this command, makedir, allows you to make a directory. And so you need to provide a directory name for the directory that you want to make. And then I just have a note here that anything that you see in these manuals that are in brackets is optional in any part of the command. So optional being this -pb or -m, those are optional flags that you can add to this command. And any part of the command that's not in brackets, like the directory name here, is going to be required in order for the command to run. Oh, I gave you this answer. But I guess to test our listening skills, for the make dir command, which parts are optional and which are required? You guys could type your answers in the chat. Go ahead and type your answers in the chat. So for this make dir command, which parts are optional and which parts are required? Yeah, you guys type your answers to everyone if you're comfortable with it. But so what he said, I'm not sure if you're comfortable with me saying who, said that brackets are optional, which is true. So that would be this -PV, -P or -V or -M. Those options are all going to be optional. Yeah. So Ty, you said make dir name is required. Yeah, exactly. And we're going to see how that works when we run things. Yeah. Thanks, guys, for answering. Next question. Do you notice how the different parts of the command are separated? You guys type your answers in the chat. Spaces. Yeah, right, with a space. Exactly, with spaces. So on the command line, spaces are very special. They're used to know how to properly separate distinct parts of a command. And because of this, it's not going to be ideal for a file or a directory for those names to contain spaces. So it's actually better when you're writing files or directories that you want to access in the command line. It's better to have the names of those files and directories use dashes or underscores instead of spaces in their names. So just as an example here, if you want to write a text file called example test1, .text, it is better to write it, what you see here at the beginning, example underscore test1.text is going to be better when accessing that file on the command line than if you were to write it with a space instead of an underscore. So running Unix commands, before we run the make dir command to make a new directory, we first would need to decide where to make the new directory. And so on computers, as many of you guys already know, files are organized into directories or folders. And when you open a terminal, it's going to open to a particular directory that's on your system. And that's going to be referred to as your working or your current directory. And you can see what your working or your current directory is by executing a command called pwd, which actually stands for print working directory. So in the example I'm going to show below, you'll see the output of the pwd command on my system. So I did all of this on my local computer to show you guys what these things look like, and then we're all going to be doing it together after lunch. So on my system, when I opened up a terminal and I typed pwd, I saw that I was in this location called /user/acerabia. And so what do you guys think is the name of the current directory that I'm in, or the current folder that I'm in? You could type it in the chat in the example I'm showing here. Yeah, acerabia. Yeah, so my current directory is going to be this acerabia directory, the one that comes at the end of the last /. So you can also list what's in your current directory with a command called ls, which actually stands for list. And I'm going to show you what that looks like on the left here. So when I type ls here, you'll notice that in my acerabia working directory, I have a list of these files and documents. And you can also navigate to the user acerabia director using the Finder window. And so for the next few commands, I'm going to show you guys how things look on the command line and how those same things look now in the system that most of you guys are probably used to, like through a Finder window. So basically, if I go to a user's acerabia folder in Finder, this is what I'll see. And I think I have a question here. So do you notice any similarities between the files that I'm seeing with the ls command on the command line compared with the files that I see in my Finder window when I go to that same location? You guys type it in the chat. Yeah, they're the same. So this is just two ways of doing the same thing. So here on the command line, checking out what folders are in my current working directory in a Finder window, which most people are used to. If you go to that same directory and just look to see what's in this window, it's the same thing as running an ls command in that location on the command line. And that's actually what your computer is doing behind the scenes. So similar to how you can navigate to a different directory or folder within your current directory just by double clicking on the folder icon in a Finder window, you can also use the cd command to change directories in your terminal. CD actually stands for change directory. And so in some of the examples below, we're going to navigate to the desktop using the command line on the left, and then I'm going to show you what it looks like in Finder on the right. So here, you'll notice at the top, I ran this command called cd desktop. And I guess before I get into that, let me just go back. Here, and just so you know, when I LS'd in here, you'll notice that desktop is one of the locations that I can click to within my Aceravia folder. So I see desktop there, and you can also, of course, see desktop in Finder here. So that's just what I'm doing when I write cd into desktop, so that folder exists in my Aceravia location I'm currently at. And now you'll see that when I run this pwd command or print my working directory has now changed to the desktop. And now similarly on the Finder window, I could also double click that desktop folder, and that will bring me to my desktop. Same thing as running cd desktop in the command line. I gave this away, but what is the working directory now? Yes, yeah. Yeah, Mark beat everyone to it. It's a desktop is where I'm at now. So again, the last name that you see in the slashes with your pwd command. I also kind of gave this away, but how are the directories distinguished on the command line? Yeah. Well, slashes, yeah, /. So these / here are what separates the directories on the command line. So we see we have this top level directory called users. Under that directory is a subdirectory called Aceravia. Under that directory is another subdirectory called desktop. And so that's how those individual directories are separated through those /. So now we can see what's on the desktop now that that's where we are using the ls command in the terminal window. And so here on my desktop, before I made these screenshots, I cleaned up my desktop. It's normally not this clean. But I ran ls, and you can see all the directories and files that was on my desktop at the time I ran this. And then on the right here, similarly, if I double click on desktop, we see now in the Finder window that I'm on desktop. And just like what we saw in the previous location, we see that taking a look at what's in your desktop using ls on the command line, you'll see the same list of files and folders as you do when you double click the desktop directory in your Finder window. Technically subdirectories, that's right. So compare the content on the desktop in the terminal with what is shown in Finder, and you'll notice again that they match up. So really double clicking within your desktop, underneath the hood, it's actually running these cd commands to navigate within your file system on your computer. So now that we've set the desktop as our working directory, we're gonna use this makedir command to create a new folder on the desktop. And just to recall, in the manual for makedir, in that synopsis section, it shows how the command should be run. And so in the example that I'm going to show, we're going to make a directory titled My Directory on the desktop using the command line, and then view what's on the desktop using both the command line and Finder. So here on the left, keep in mind that I'm still in my desktop directory, or subdirectory, since it's below several other directories in the file system. And within that desktop directory, I'm going to make a new directory with this mkdir command, and I'm going to put the name of that directory as my directory. And now when I run ls, as you saw in this window just popped up, you'll see that I now have this new directory here called my directory that I just made. And now because I made this within my system, even if I navigate to the desktop on my Finder window, I should see that my directory is now there in my Finder window as well. Because again, it's looking at the same location within your compute system. And so just making a note here that make dir command is equivalent to if you were to right click or click on the icon within here and click create new folder in Finder. And again, that's actually what Finder's doing behind the scenes when you right click and click create new folder. It's running this mkdir command. So I got into how to create variables on the command line. And so there are going to be times when we'll need to set our working directory to a folder that's going to be deep within a directory structure. So rather than having to navigate one directory at a time like you would in Finder, you can navigate directly to your folder of interest with a single cd command in the terminal window, as long as you have the explicit path to where that directory is located. And so for example here, you'll notice that I start in with pwd. So in this example, I start in that Asaravia directory, and then I'm going to cd using a full path to the directory that I just created in the previous slide called my directory. So note that I'm going to have to go a few levels deep to get to my directory, but rather than having to navigate one directory below at a time, I can just run this cd command and put this explicit path separating the directory names with a /, and this should bring me to my directory folder that I just made in the previous slide. So after running that cd command with the explicit path to my directory, I then ran a pwd command to print what my working directory is now. And you'll notice that indeed I'm now in my directory, which is the folder that I made in the previous slide. So if there is a location that we need to visit often, rather than writing out the explicit path every single time, we can create a variable that contains that explicit path. And in Unix, you can do this using an equal sign to assign the path to a variable name. And so that looks like this. So you'll notice again in this example, I'm starting back at my Asaravia folder, and then I am going to run this command. It's called mydir, which is the variable name that I made up. And I'm going to make mydir equal to the path to my directory. So mydir is going to be equal to this explicit path to the my directory folder. And here I'm going to run this command echo, and I'm going to call that variable mydir. And when I do that, you'll notice that it prints out exactly what I saved mydir as. So this explicit path to my directory. And now when I run the cd command, I can cd and hold this variable mydir, and now when I print my working directory, you'll notice that after running that cd or change directory command, I'm now in my directory. So a couple of questions about this. What command was introduced in the example above that I haven't talked about yet? You guys type your answers in the chat. Yeah, echo. So echo simply just prints whatever it comes after the echo command. And so do you want to ask this next question here before I get any further? What was added to the variable name when using that variable in Unix? So what did you notice that I have to add to my variable name? Yeah, I had to add a $sign in front of it. Oh, Mark, you got a %sign. So we'll actually, that's in, is that Python that holds the percent for variables? Yeah, in Unix, it's the $sign that's going to hold your variable name. And so you'll notice that I can call my variable, what's stored in my variable, anytime, so long as I put a $sign in front and the variable name immediately after following that $sign. So now when creating variable names, there's a few things that I'd want you guys to keep in mind. Is you don't want to name your variable after a common function or a variable that's already built into the coding language that you're using. And we'll get into that a little bit in the Jupyter Notebooks. You want to avoid using spaces in any characters other than letters, numbers, dashes, and underscores. Anyone remember why that is? Why we want to avoid spaces in weird characters? You guys could type it in the chat. Why would we want to avoid spaces in our variable names? Yeah, program microcommutes, separate command. Yeah, so the spaces are very special on the command line, and right. And it tells the computer how to read the command. And so we want to be very careful with spaces. So when creating a variable name, we want to make sure that variable name does not have a space, or else the computer will read it as two separate things when it's just supposed to represent one thing. So make sure that when you're coming up with variables, you avoid spaces and any weird characters because that will confuse the system. Another thing about making variable names is you want to choose informative, memorable, and short variable names. So I have a quick little example here. Is what would you do if you wanted to create a variable to store gene expression data from, say, Drosophila melanogaster, commonly known as fruit flies, that were grown at 10 degrees Celsius, 20 degrees Celsius, or 30 degrees Celsius. So I just kind of made up a few different variable names, and I'm just curious which names below do you think would be good variable names to use? You guys can put your answers in the chat. 6, my data. Number 2, DML, GEDT. Any other suggestions of which of these 8 examples would be a good thing to use for a variable name for this Drosophila melanogaster gene expression data? Two, a lot of votes for 2. Any other suggestions of what we could use? Okay, I'll go ahead and just highlight it here. So 2 or 3 of these options would be good. And the reason so, this first one here, you see it's very long and cumbersome, so not a great thing to use if you're trying to shorten something with a variable name. 2 and 3, you'll notice, are quite informative. They tell you the name of the species, whether the scientific name or the common name, GE standing for gene expression data, DT standing for delta T or delta temperature. So these are nice and short, no spaces, no weird characters, and gives you quite a bit of abbreviated information about what's contained within that variable. Number 4 here, you'll notice that it has these little degree symbols in there, which can be cumbersome and confusing to the computer, so it might not recognize that as a variable, so we want to avoid that. Echo you wouldn't want to use, 1, because it's not informative, and 2, because it is already a command that's programmed into the Unix system, as we just learned in our last slide. My data, the reason I wouldn't use my data is because it's vague, and so I wouldn't really remember what information I stored in my data. So if I'm dealing with a lot of different variables, for instance, if I had one that just said my data, I might be unsure of which data if I'm dealing with a bunch of different data sets. The DML, GEDT, so a couple of issues with this one. One is it's nice that it has no spaces and it is informative, but having these $signs in between, remember that Unix recognizes a $sign as a variable coming right after it, and so it'll get confused having these multiple $signs within this one phrase. And then, of course, number 8 is no good because it has spaces in it. So I do want to just do an overview of Jupyter Notebooks. I know that I don't think any of you have experience with Jupyter Notebooks, so hopefully we will get you to love them as much as we do by the end of this. So throughout this bootcamp, we're going to be running several of the commands that I just went over. However, working directly on the command line can take some time to get used to. So we're going to be using Jupyter Notebooks to run all of our commands. Jupyter Notebook was created as part of Project Jupyter. Link is right there in the slides. And it's a web application that allows you to create documents that have both a narrative text, so you can describe what you're doing, and also it has live code, so you can actually run code right in the Jupyter Notebooks. So instead of having to open up a terminal, you can run things right there on the Jupyter Notebook. And this is just an example, actually, of the volcano plot section, which we're going to get to towards the end of the boot camp. And as you'll note, this is a screenshot taken from a Jupyter Notebook, and you see that we have a section here with text describing what you're seeing. And then we have a block here that we're going to refer to as code blocks that actually contain a command that's being run. And then it's nice because you can run that command directly on the notebook, and then it'll generate the output file right there for you underneath the code block, as you see here, an output volcano plot. So super convenient. Some additional advantages of Jupyter Notebooks is it facilitates sharing code and results between groups. For example, you guys are all going to be able to use these Jupyter Notebooks again when you teach this at your home institution very easily. And also is ease of publishing your code. So when you publish your completed Jupyter Notebooks, you can see it's very transparent with all the code that was used and the outputs that were generated from the specific code that was run. And it also allows for reproducibility. So if you give the same person the same Jupyter Notebook, and so long as they have the same versions of all the tools installed, you should get the same exact results. The next thing I want to go over, and if you guys have questions about Jupyter and stuff, we're going to get into that a lot more after lunch when we start our hands-on portion. So we'll be able to answer questions, and you guys will learn how to navigate the Jupyter Hub environment. So the next thing I want to talk about to get you guys familiar with is a compute cluster. And so when we execute commands in our Jupyter Notebooks, we kind of set up like a mimic simulated compute cluster to be able to run those commands. So what a compute cluster is, it's essentially a set of servers that are like computers, and they're all connected, and each server is used for a specific purpose. So below is a schematic of a relatively simple cluster containing 4 servers, also referred to as nodes. And in this small example of a compute cluster, we have 1 head node up here at the top, and then we have 3 compute nodes, snap, crackle, and pop. And so a head node is the server that's going to allow you to connect to the cluster. So when you log into a cluster, whether it be with us or at your own institution, if you have a compute cluster there, you would be logging into the head node. So the head node, because it's responsible for logging people in and managing which jobs are run, you shouldn't run any commands that require a lot of computational resources on the head node. And of course, I said, why do you think that is? And I just gave you the answer. So on to compute nodes. Compute nodes are servers that are used to actually run the commands. So the compute nodes are where all the commands, the programs, and any scripts that you want to run are going to be run through. So the compute nodes usually contain more computational resources than the head node. There are often multiple people logged into a cluster at any one time, and they're all going to want to run jobs. So this is going to be a problem for the servers in the cluster. Why do you think that is? Why would it be a problem if you got a bunch of individuals using the same compute cluster running a bunch of different computational jobs? Why do you think that that could potentially be a problem? You can type your answers in the chat. Limited space, yep. Slows down processing time, yep. Could lead to a clog, absolutely. Yeah, so you guys are all right on the money. So I have a hint here, which I probably should have put up before. You guys all got it. So think about what happens when you try to run a bunch of applications on your personal computer. Things start to slow down. Sometimes your computer just freezes. And so if you can imagine multiple people each running several applications on a server, that same thing could happen. Everything you guys just pointed out, they could run out of space, they could run out of memory, there could be a jam in the system, and the whole cluster can just kind of shut down, or at least the nodes that things are trying to be run on. So to avoid multiple people running jobs all at the same time and risk freezing the servers, compute clusters are usually set up and equipped with a job scheduler. And so rather than executing or running a job or a script, I'm going to use those terms interchangeably, users can submit their jobs to the job scheduler. And the job scheduler is going to check each compute node to see if there are enough resources available to run the job. And so the job will begin running on one of the compute nodes only if it has enough resources available to run that job. If there isn't enough resources available to run that job, then the job is going to get put in a queue, and it won't start until enough resources become available on one of the compute nodes. So during this boot camp, we've kind of simulated submitting jobs to a simulated cluster that we have that's running a simulated job scheduler known as Slurm. And so I just want to show you, so there's going to be in RNA sequence analysis, there are some jobs that require quite a bit of resources and require quite a while to run and process. So those jobs we're going to be submitting to a job scheduler, and we'll just see kind of what the output of that is to make sure that the jobs are loaded up in the queue. So I want to go over you guys what a Slurm script looks like and what it's going to look like for us to submit these jobs to the job scheduler. So this is an example of a Slurm script. This is a special type of Slurm script called an array script. And so when we process RNA sequence data, there's going to be, we have our processing pipeline that we're going to want to run each of our samples through. So prior to combining the data from all the samples together, we first have to process each sample to run the jobs within the RNA-seq analysis pipeline. And so we're going to need to run the same exact job on all the samples in our study. And so rather than having to write and submit a script for each and every sample that's going to be running the same exact job, the only difference is that the input files will be coming from a different sample, you could set up what's known as an array script, and then the Slurm job scheduler will know that you want to run the same exact job or same exact command on multiple different inputs. And so this is super helpful because when we want to run one job, for instance, when we're trimming our data, which is one of the first steps in the RNA-seq pipeline, we're going to trim our data exactly the same for every single sample. And so we're going to run it through the same exact command. And so setting it up this array script, we only have to submit one script and then it'll go through and process all of our samples using those same sets of commands. And so I'm going to break this down and show you what each part of this script is. Starting first with that top section. So at the top here, this #! bin bash is telling Slurm that we are running through a Unix shell bash interpreter. So it's telling it what kind of system we're running these commands on. Anything with a hashtag that's blank, it's just a spacer. The computer doesn't read anything into it. Anything that starts with #sbatch is going to be, I have these actually written out here for you. Anything that starts with #sbatch are your actual Slurm commands. So anything when Slurm reads #sbatch, Slurm knows that it's telling me something about the job that I'm going to run. And so this first option here, -- job name, is going to tell me what the name of the job is. And so you can name this whatever you want. In this example, this actually came from one of the scripts that I ran to generate the pre-processed data for this bootcamp. So this is actually running a GeneLab data set, a tool called RawFastQC. So that's what I named the job. This next sbatch command or Slurm command, -- output, is going to tell the system where to put the standard output. And so what I'm telling it here is to put it within a directory called RawFastQ outlogs and to name each file, because this is an array, which means that it's going to be running the same command multiple times, once for each sample. And so these codes here, %A and %a, is telling Slurm that in this file name for each sample, I want you to give me the Slurm ID, because all Slurm jobs will have a Slurm ID. And when you submit an array script, it'll have a main Slurm ID, and then it'll have a sub ID for each job that is running within the array. And so that's what those are standing for. This next command here is a flag called partition. And so a lot of clusters will be set up with different partition, and that's how Slurm knows to run your job next versus to put it to the end of the queue. And so we actually have a partition called priority to allow jobs to jump to the top of the queue. So that's what that's indicating there. This next option here called --mem is going to tell Slurm how much memory, so how much RAM is going to be needed to run this job. So this way, when you submit this script to the job scheduler, it reads these sbatch commands and it says, okay, I need to check the compute nodes to make sure there's at least, these are in megabytes, so at least 6,000 megabytes or 6 gigabytes worth of memory available. So it'll scan its compute nodes and see if any of the compute nodes has 6 gigabytes available that it can reserve to run this job. And if it does, it'll run it. If it doesn't, it'll go in the queue until there is that amount of memory available. This next option here, dash dash array. So this is telling Slurm that this is an array job, meaning that I want you to run the same command, the same script on multiple different input files. And here specifically, I'm telling it to run 12 different times for 1 through 12. And I'll get into what those 1 through 12 are going to correlate to in a second. This next set of commands is some Slurm or some job schedulers are going to be hooked up to be able to access email. And so that's nice because if your job is submitted to a queue, you might not know when that job is going to be completed. And so what these options do, it'll tell Slurm what email address to send a notification to. And then this last one, mail type end, that's telling Slurm to send an email to this email address when this job has completed. So to give a notification when the job is done, and then you'll know to log into your system and the job is ready. This next set of the script, I'm just going to go through this here. Some of this stuff is just how I personally set up scripts to keep track of things. So I'll just go through what these are. So this first part up here is just instructing Bash to use the user profile settings. Here's this echo command that we went over previously, and this is so that in my standard output for this job, I always have the title of the job printed out in the actual output. This part here, I like to record timestamps for my jobs. So before I run my command of interest, I will run these commands here that are essentially just recording the start time. And then you'll see at the end, I have a set of commands that indicate the end time and then calculate how long the job took to run. This here, echo hostname, this $sign hostname is actually a variable stored within Unix, and it'll print the name of the server that the job is running on. So if you have multiple, I got a question here. I'm sorry, the last two commands I didn't catch. My audio cut out. Mark, what part did you miss? The last slides, okay. Let me just go over to the previous slide here. Is this what you missed, Mark? Okay, great. Yeah, so all of this is available in the slides. So we'll go over it again in the Jupyter notebook too. But yeah, all of this written out is available in the slides on the Google Drive and on GitHub too. So maybe during lunch, if you want to go back through and review it, it'd be great. Okay. Let's see, we were here. Yeah, so this, the reason that I think that this is valuable to record the host name or the server that the job's being run on is because as you saw in the cluster setup, we have several compute nodes. And your job can run on any one of those compute nodes. So when you have 100 samples in a study and you're setting up this array script for 100 samples, those 100 samples can run on all the different clusters that you have or all the different nodes that you have in your cluster. And so if you end up getting like 20% of your jobs fail, now you want to go in and troubleshoot. If you notice that all 20 jobs failed were all the ones that ran on a particular compute node, now that can tell you, oh, maybe it's an issue with the compute node and not necessarily my script. So that's why I like to record that in all of my standard outputs. The other thing here is, as I mentioned, this is an array script. So it's going to run the same command on a bunch of different input files. And so I just like to keep track of which job this output file is being run on, or which number in the array is it being run on. So this is another variable that's stored within Unix or within Slurm, and the Slurm array task ID allows you to print the Slurm job ID number to your standard output, so it'll be stored in your output file. This command here is activating a required Conda environment. So Conda and Anaconda is a system to install bioinformatics tools. And you can install these tools in isolated little environments. And so you want to make sure that you're activating the environment containing the tool that you want to run. And so that's what that line does. These commands here are creating variables for the input directory, which is going to be the directory that has all the input files I'm going to need for the command, and output directory, which is a directory that was set up on my system to output all of the files that are generated from the command. And then this part here, I'm actually creating a variable called sample, and that variable is going to be dynamic. So that variable is actually going to be the sample name of all samples listed in a file called samples.txt. And what this part of the command doing here is it's just telling the system to associate each sample listed with a different slurm ID, so that the first sample listed in the samples.txt file is going to be associated with array 1. The second sample listed is going to be array 2, the third sample listed array 3, and so on. And so that's how it's going to store the sample name in a variable, and it'll go through the samples.txt file based on which job in the array that we had set up. And if you remember from the previous slide, we have 12 jobs asked for here, which means it's going to be 12 samples that we're going to be running this same command in. This next part here is I like to keep track of what sample is actually running. And so what I do is I just use that echo command again to print out the variable stored as sample. And you'll note that there's something a little extra when calling this variable. Because this is a variable changing and associated with the number in the array, in order to call it properly, you actually have to put a $sign and then the name of your variable in brackets. So that's why you see it like that. I always like to know the version of the tools that I'm using. So for some tools, the automatic standard output of that tool will tell you the version of the tool that's being run. Unfortunately, that's not the case for all tools. And because there are changes that are made in tool versions as new versions are released. And so I really want to make sure that I know which version of the tool I'm running. And so I always put a command in my scripts to ask for the tool version. So this particular tool is called FastQC, which we'll get into in great depth tomorrow. And an option for that FastQC tool or command is version, and it'll print out what the version is of the tool. And then kind of the end of this big Slurm script here, I actually put the command that I run. And I actually hold all of my commands inside of a variable. And so this command is fastqc. I have an option -o here to indicate the output directory. We're going to get into that a bit more tomorrow. And then another option here, a positional argument, which we'll get more into after lunch, of where to output or where to the input files are. And so you'll notice that I'm calling that variable of sample. So this is what the tool is going to look for in the input directory, is the sample name and then this fastq file, which we're going to get into more in the bootcamp. And the reason that instead of just running this command directly on the line, the reason that I store it in a variable is so that I can use the echo command to print the exact command right back to me. So this will print out the exact command as it's running with all of these variables filled in. And then echo with blank quotes, that's just giving me a space in my standard output. And then this command called eval, it tells it that this variable called call is an executable variable, and eval will tell it to evaluate or to run that command. And so then at the very end of my script, you'll notice again we have a space here, and then I print out the end time of the command, and then I go through and do calculations here, so that way it tells me how long the command ran in seconds, minutes, and hours. So we'll see all this starting after lunch.